Good morning, everyone, and welcome to the morning session of our second day of our wonderful meeting. And our first speaker this morning is Ren Yeats. They work at University of Waterloo in Canada, and they're going to tell us about some combinatorial structures in quantum field theory. And we already have some beautiful pictures of some of them.
All right, thank you very much. Thank you very much to the organizers for inviting me. Of course, these conferences take a long time to bring from conception into reality, and they invited me back when ostensibly I fit the topic of the conference a little bit better, but that's all fine, and thank you to them. I'm going to talk about, so here are a whole bunch of combinatorial structures. These are all ones that I have personally been involved in. There are many more places where combinatorial structures show up in theoretical physics of various sorts. I'm going to focus on quantum field theory today, and I'm going to focus on some particular parts of quantum field theory that I have been involved in myself, but there are, of course, many others. There's things here that are not quantum field theory. There's some representations here of causal set theory, which is something I've become interested in recently. And of course, there are lots of other combinatorial structures that show up in theoretical physics as well. You can think of pretty much anything in statistical mechanics, say 6-vertex model, just to have one concrete example. You can have the whole story of the Plabic graphs and that, which I haven't, well, I represented only a very small part of that here. But today, I want to talk about quantum field theory, and there's a nice Feynman diagram up here. So I'm going to work in perturbative quantum field theory. So here's a Feynman diagram. I'm going to briefly talk a little bit about how I want to think about sort of using some generating functionology to understand Dyson-Schwinger equations, or understand some recurrence equations for the quantum field theory. I will briefly mention some tricks I have to solve them that are a little bit special. Solve them as a series solution, so not really if you're a physicist. But then what I actually want to talk a little bit more about today is some of these graph invariants with Feynman period symmetries. And so that's sort of this part of the story. But, you know, many things, and I think they're all interesting. I don't know if you think they're interesting. Hopefully by the end, you will think they're a little more interesting. Okay, so what is the story? If I want to do the cartoon of a scattering experiment, what is it? Well, you got some particles coming in, and you know what they are because you made them, because you made the beams. I mean, I sure didn't, but your experimentalist friends did. Okay, and then you know what comes out because you have detectors. That's nice. And again, I don't know, you have to ask your experimentalist friends about the detectors. And then something happens in the middle and you don't know what it is, right? That's the basic cartoon of what's going on in a scattering experiment. And so if you take this Feynman diagram expansion approach to doing perturbative quantum field theory, what are you trying to do? You're trying to understand what happens in the middle by summing over all the possibilities of what happens in the middle. And you can think of these possibilities in terms of Feynman diagrams where the external particles are the ones you know what they are, because they're the ones that either you made or you detected, and you don't know what happened in the middle. Okay, so you get from that, you get a Feynman diagram expansion. So for instance, you know, maybe you're interested in something like this. You've got a photon, it's going to split into an electron-positron pair, and you want to say, well, what are all the ways that this can happen? And you say, okay, well, it could just happen, right? That's like perfectly okay, it could just happen. But maybe something more complicated happened. Maybe that happened. Or maybe something even more complicated happened. Maybe that happened. Okay, and I'm used to the world where you've already reduced to connected in 1 pi, but of course, I haven't said that yet. So in principle, something like this could happen. Something like that. That's a thing that could happen, or something disconnected could happen too. You could, maybe that happens by itself, but then something else happens over here. It just didn't matter. Okay, so all sorts of stuff can happen, right? And well, that's all fine and good. And there's a whole industry of people who do the actual computations to turn those things from pictures into actual numbers so that you can, you know, compare to the experiments at CERN. You can calculate the backgrounds for the experiments at CERN and things like that. But that's actually not my background. So I started by saying I'm a combinatorics person. I started as a pure math person. So if I put my combinatorics hat on and I look at this, I say, look, I've got some series in graphs. If I start putting in the coupling constant, it looks even more like some sort of generating series for something. So I'm going to call it X because I'm weird, but you can call it alpha or E or whatever is your favorite thing to call it. I'm going to put it in by the number of loops. Okay, those all turned out to be at order X squared because I'm doing the loop number for my power of coupling. Okay, so now it's really starting to look like some kind of formal power series with coefficients in something, I don't know, some algebra of graphs, ultimately some Hopf algebra of graphs. So that's nice. And so we can try to understand these things better using generating functionology, using tools of enumerative combinatorics. Okay, so let's think about one possible example of how that could work. Now, to do a nice, clean example on the board of how something like that could work, I want to simplify a little bit. I'm no longer going to try to make all of the graphs with some particular structure. Let's just try to make some of them that are nice in some way, that are built up in some nice way. And so this is going to connect back to something over there. Let's think, okay, and I'm just doing diagrammatics, so I'm going to draw them as quantum electrodynamics diagrams, but they're drawn over there as Yukawa diagrams for a reason. Okay, so let's think about this. Let's say I want to have corrections to the fermion propagator here. Okay, but now I'm not going to look at all of them. I'm just going to look at some of them because I want to keep it simple for the moment. So what could happen? Well, nothing could happen. That's fine. What else could happen? Well, it could be that something like this happens. And now in the middle, let's just look at what happens if I put copies of the same little bubble. So there's this little one loop guy. What happens if I just put copies of that inside itself in all possible ways? But not just as a rainbow. So if you haven't seen the physics side of this story before, the guys like this get called rainbows for obvious reasons. But there's more I could do than that. I could also, you know, put them like this inside, right? And I could do combinations. So, you know, something like this. So what does that end up being? Well, that means that in here, I could have any number of these guys, right? So, well, and I'm going to write that with the other kind of blob. Okay, and there's an X because there's one extra guy there. And what is this guy? This is supposed to be, well, any number of them. So this is supposed to be either just one of them or none of them. Could be none of them, or it could be one of them, or it could be two of them, or it could be three of them, etc. Okay, so what is that? That's just a geometric series. So, well, if you forgive a little bit, that's like 1 over, well, 1 minus blob. Okay, forgiving the notation for a moment. Okay, but you know what? Let's just think about this just purely in terms of generating functions. What's really going on? I'm making some class of trees. Here's where I should get a color. Because there's some trees here, some dual trees. Okay, so this guy, there's just the one thing. So it's that guy. This one this rainbow shape turns into a ladder. 1, 2, 3, 4. This guy, well, there's this outer guy, and then there's these guys, and they're all inside, but none of them are inside each other, so that makes a little tree like this. And this one looks like this. And you'll pretty quickly see that what you're building is plane trees, what are often known as plane trees. So trees with an order structure on the subtrees. Okay? Well, I know how to do that. If T of X is the generating series, ordinary generating function of my trees, so just sum over all of the trees weighted by what was the loop number here and is the number of vertices here. Well, what happens? There could be nothing at all. Okay, I'll just write that as 1. Or there could be something where I put a new root on any number of things below it. And I'm going to use B plus for add a root. So looks like this. If you have trees, then that. I put my roots at the top. I don't know. That's depending on what tradition you were raised in, you may or may not put your roots at the top. You might prefer them at the bottom. It doesn't really matter. Okay, so, well, the 1 is already there, and I'm going to make this a minus just to make it all work neatly. I'm going to get something like that, my geometric series in my trees. And that'll build you all these guys. Well, I put a sign in, so they're going to come with a sign now, but it doesn't really matter. Okay, and so this is a story that you can play. There's any kind of tree that you can make as some composition of this, the generating series of the tree, with any other formal power series. Those are called simple tree classes. They all sort of make sense in this context, and you can play that standard generating functionology game. Okay, but that, yes. So usually in this sort of story, so notice, so yeah, I will draw you an example of overlapping. Well, here's one, I guess, but here's an example of an overlapping subdivergence because there's this guy and that guy. Usually you want to then think of the sum of all the possible insertion trees that would make it. And note in my Dyson Schwinger game, I'm typically picking cases where that's under control. But yeah, you want to sum over the different possibilities. Yeah, that's a standard solution, standard way to go between the Feynman diagrams, which are more complicated than trees, definitely, and the trees which are showing the insertion structure. Okay, so you can play this game, and this is basically a tree enumeration or graph enumeration game. Yes? Yep, so I'm putting my roots at the top, so they're upside down trees. Computer scientists often draw their trees this way, and the joke is computer scientists live in caves, and so the trees are actually things that are growing from the ceiling of the caves, and they don't have like proper trees. Anyway, that'll help you remember. My roots are at the top. It's not for any particularly good reason. Okay, so this is fine. You can count stuff. You can play more sophisticated versions of this game and do zero-dimensional field theory, which is a really cool tool for counting graphs. You can play all sorts of games in that direction. But if I'm going back to my particle accelerator story, I don't actually just want to count Feynman diagrams. I want to actually know the numbers and know the sum of those numbers. And so that's where what you really want is not just this story, but an analytic version of it that has the Feynman integral in it as well. And I will write down just one that has this shape as a concrete example. Now, I apologize to physicists because I have a weird normalization that you will not like, which I also don't fully, not worry about it. I'm writing this down, but this is one of these don't worry about the details things. And I'll explain what I want you to get out of it in a moment. Okay, so what is the idea here? And I will explain by color coding. Let me just get a third color. Because this is a very simple example of a sort of Dyson-Schwinger equation that you might see if you were actually doing some physics here. So L here is going to be log Q squared over mu squared. And now I'm thinking about this graph. Well, I've not written QED Feynman rules there. So if you're in the know, I've taken I've taken a suitable contraction, but with a suitable contraction, that's going to be Yukawa Feynman rules. But what you want to think about is a momentum Q, sorry, not Q squared, Q, going through this diagram. You want to think of a K along this and K plus Q going that way, which I guess means I've got this one oriented that way. And then Q is coming out again on the other side. So that's nice. Oh, I didn't grab the right color. I grabbed 2 copies of the same color. That's not very smart of me. All right. Here's how you want to think about this. There's an integral kernel, which is this part. And that is corresponding to the B plus, because that's where I added the new root, or equivalently, added the outermost loop. And there's a recursive insertion, which shows up as a 1 over, and that's this. And that's where I'm adding in all of the guys that are inside, whatever they are. All right. And what else? Well, what the heck is this part? This part's actually the renormalization. Because I'm doing a momentum scheme renormalization, so I'm renormalizing by subtracting at some fixed renormalization point, which is this mu squared. And so then the log Q squared over mu squared, if you think about the dimensions a little bit, you'll see that it actually only depends on this L, and that's the log energy, basically, going through the diagram. No, I'm imposing, it's one of these things where I'm saying that the value, so notice I've said take the same integrand and subtract off at this particular reference scale. So that means that you're forcing it to be 0 at that reference point. So you're taking that as a reference point, but there's no cutoff. I'm still integrating. I guess I didn't write what I'm integrating over, but I'm integrating over the full 4 Euclidean space. I've written this in Euclidean. Yeah, so the L is coming from, notice this is definitely a function of Q, which is the external momentum, and it's a function of mu. And if you think about it a little bit, and actually you need a normalizing factor out here that I've forgotten, but if you think about it a little bit, you'll see that actually it doesn't depend on Q and mu separately. It only depends on Q squared over mu squared. And it's just convenient then to put it in terms of log Q squared over mu squared. Okay, so the point is, not the details of that, but the point is physicists look at examples like this and they want to compute them because that lets you compute, well, some useful special part of the perturbative expansion. So that is a useful thing to compute. And the shape of the equation, the way the pieces go together, exactly mirrors the shape of the tree equation. And so you can hope to use some combinatorial techniques to solve this equation too. Well, now I'm being hand-wavy about what I mean by solve. Because in principle, like, I might want an analytic solution to this thing, but I'm not really an analyst. So you already should be very suspicious that I'm probably not actually solving this equation. So what am I really going to give? There's a singularity at the origin, as you would expect when you think about these things, but I can have a series expansion. It'll be an asymptotic series that will be the solution to this thing. And the asymptotic series, I could hope for a nice way to index it in terms of combinatorial objects. Now, your first thought might be, wait a second, there's already a nice way to index these series in terms of combinatorial objects. That's what the Feynman diagram expansion was at the beginning. However, that's not actually what you want in the end. I mean, it's good as far as it goes, but each diagram is contributing something quite complicated. It's Feynman integral. I want a combinatorial expansion where each piece contributes something really simple. And I can do that. And that's two of these things over here. Yeah, I think the nicest way to think of it is the energy level. But then if you think about the renormalization group flow, that's exactly your scaling parameter. Yep. So that's what these guys are. So these are rooted, this is a rooted connected chord diagram. I've marked some of the chords as being special. So a bit over a decade ago, I showed how you can solve that guy. And then in the subsequent years, we've showed how to solve lots of other Dyson-Schwinger equations using an expansion in terms of these guys. And now more recently, and I think this is really the better answer, but I put this up here. Well, I put them both up here because they're both nice combinatorial objects. But recently we realized we can rewrite this in terms of what we call binary tubings of rooted trees. And here is an example of a binary tubing of a rooted tree. And this one is really nice because the proof here, and I can say this because it's my proof, it was absolutely disgusting. In the sense that it was a recursive thing. You show the base cases agree, you show they satisfy the same recurrence. Unfortunately, you had to do it twice. There's two variables there, and it was just hideous and had no insight. Whereas this proof really has insight, and the reason you get insight out of it is because it comes out of the Hopf algebra structure, which I mentioned briefly in passing, and some other people in this room are excited about Hopf algebra structures. This is my only sort of representation of the Hopf algebra structure in my picture of diagrams, but combinatorial Hopf algebras are beautiful combinatorial objects, and they do tell us a lot about quantum field theory. In particular, they tell us about renormalization. And they let you give finally a nice conceptual proof in terms of tubings. So can solve, I'm not going to tell you how this goes in terms of tubings of rooted trees. And the benefit of doing it that way was, first of all, it was just a much more conceptual proof, but also it finally let us generalize in some directions that had been quite hard to do when the proof was just a disgusting, you put your hands in the guts and you do this, and then eventually the proof pops out. It's not as easy to generalize as the conceptual one. Okay, so that was sort of one thread where combinatorics does some cool stuff. But I think what I really want to spend the rest of my time on is this other thread. So comments before I move on? Yes. They don't have to be. I use those examples here because they're simpler. So if I work with a quartic interaction, then of course the Dyson-Schwinger equation itself is more complicated. But you can still rephrase it in terms of trees, where again you have to resolve. Also, you have more problems with overlapping subdivergences. So you have to resolve the overlapping subdivergences. Technically, there's more to do, but the basic framework can work in that case too. Trying to keep something simple for the board. Yes. Yes. Yeah. Now notice, I mean, obviously, if I could just solve these things outright, then whatever, we'd be done. There's a lot of input that still has to go in. Because, well, one of the pieces of input has to be, basically you take a regularized version of the integral of just the primitive. And then I need to know about the terms, like I write the solution I get is in terms of the coefficients that appear in that regularized integral for just the primitive diagram. And so that would be true. So when you have a more complicated theory, that's one of the ways you're going to see the complications actually showing up in here. You can think of this as capturing the combinatorics of how the pieces, the numbers that would show up in the regularized integral of your primitive diagram are then being recollected to go together into your non-primitive diagrams. And that part holds true in a non-abelian theory, in any theory. Yes, there are, yes. But But a lot of, yeah, you still have a lot of the same basic story. But yes, there are many complications, and that is one of them. Okay. I mean, who knows what will come in the future. I mean, I'm a mathematician, so I would rather stake my claim that if we understand more deeply the underlying algebraic and combinatorial structures and analytic structures, then I hope that that's the way we can actually integrate all of these things eventually. But I mean, I have no real evidence for that. That's more a case of my tastes. And that's why it's good that there's many of us who are interested in different directions, and we'll see who ultimately gets it. Okay. Do people want to keep the pictures? Do they like those? Then I'll keep writing. Because as some of these questions have alluded to, you still need to know there's numbers that come out, right? There's numbers that are not purely combinatorial that come out of the Feynman integrals. And the first ones that we sort of famously know about are multiple zeta values, but of course you get more complicated things as well, interesting elliptic integrals, things that are coming from L functions of curves, cool stuff, right? So we still need to be able to look inside the individual diagrams. So now let's look inside. Feynman integrals. And the numbers they give. And some of these pictures are up here for that reason. So looking at this from a sort of with your algebraic geometry hat on is something that one of the threads that led to that was some computations that in the 90s, Dirk Reimer and David Broadhurst did in a phi-4 theory. And so here's a nice 4.54 graph, and here's another one. And I wrote these ones up specifically because that zigzag family has a proven known expression in terms of odd zeta values. And this one is the first one that gives a non-trivial multiple zeta value, so one that's not just a product of two zeta values. So if you are going to the number theory garden party and you want to say cool number theory words, those are some of the words you want. Multiple zeta values are really nice numbers that, well, they won't impress all your number theory friends, but some of your number theory friends will be impressed. And so you can go to the number theory garden party and tell them about how those zigzags are giving you single zetas and that guy is giving you some multiple zetas. The point is the numbers you get out of their Feynman integrals are numbers that certain mathematicians think are really cool. And why do mathematicians ever think things are really cool? Because they have cool structure, right? That's how mathematics works. Okay, so I want to now define a few things. So I'm finally going to write something actually somewhat rigorous. So I am now going to, for the rest of the talk, actually look at that case. So I'm going to be interested in a graph, which is 4 regular except for the 4 external edges. So how am I going to make this graph? This graph is going to be a 4 regular graph minus a vertex. Because that's how you make a 4-point graph. And I'm going to be interested in defining a few things about it. The first is the first semantic polynomial, or I often just call it the Kirchhoff, but really it's the dual Kirchhoff. So K is an arbitrary 4 regular graph. 4 regular just means all the vertices have degree exactly 4. So, and this is a graph in the graph theorist sense. So this guy doesn't have external edges. So you could think of it as a vacuum graph in phi-4 if you like. And now I remove one vertex, and then I get a graph that has almost all the vertices are degree 4, except there's 4 external edges. So I've really just said this is a 4.54 graph, but I've said it in math language instead of saying it in physics language. Okay, and now I'm going to define the first semantic or dual Kirchhoff. And what am I going to do? That's actually already on the board. It's over there somewhere. I don't know. I definitely wrote it. It's up there somewhere. So I'm going to sum over all the spanning trees. and I'm going to take a product of the edges that are not in the tree, so the edges you would have to cut to give that tree. And then I take a monomial made out of a variable for each of those edges that I cut. So that's how I build my first semantic polynomial. So, okay, I think I'm actually going to dispense with an example for a moment because I want to do something with this. And I think I want to emphasize the graph theory of it and not actually that aspect. Okay, so then what do you do? So if G is primitive, aka K is what we would call in graph theory internally six-edge connected. And what does that mean? So internally six-edge connected means so notice six-edge connected would mean that you have to cut at least 6 edges to break it into 2 pieces. Obviously, that cannot be true for a 4 regular graph because I can always just take a vertex and cut 4 edges, and that's clearly disconnected. But when I say internally 6-edge connected, I mean those are the only bad 4 cuts. Like those are the only 4 cuts, the ones that cut off a single vertex. Every other cut, every cut where each side is non-trivial, has to have at least 6 edges. And that ends up being the same as that it's primitive. You can think about that for a moment. Okay, if this is true, then I can define PG as this guy. And now again, it depends which hat you're wearing. I'm going to write it in a certain way, but if you have an algebraic geometry hat, you probably prefer a slightly different way of writing this. So morally, I just really want to say I'm going to take the integral 1 over psi squared, but I'm not going to pass my calculus class if I write that down. I better tell you what the form is. And what I'm actually going to do is do it on an affine piece. So I'm going to integrate all but one of them and set the last one to 1. And they're integrated over the positive simplex there. So if you do have an algebraic geometry hat and you put it on for a moment, you can see it's really projective, but I've just taken an affine piece because good enough. Okay, so this is a thing. It's also, you can think of it as it's the residue of the Feynman integral. So it makes sense from physics perspective. It's of course not all that you want, but it's a piece of what you want. Feynman integral. And it is a nice algebra geometric object. Algebra. But I want to argue that it's also a nice combinatorial object because it's really just made out of spanning trees. Or maybe it's not a combinatorial object because it's an integral, but it has a lot of combinatorial pieces. Okay, and to concretely show you that, I want to tell you something about its symmetries. So it has, PG has graph symmetries. Okay, so let me show you some of its graph symmetries. So that the integral converges? So that the integral converges. Okay, we're going to do this in 2 columns. Here's the K side, and here's the G side. And remember, G is K minus phi, and K is 4 regular. All right? So what are some symmetries of this? One is that if the graph happens to be planar, and its dual also planar dual also has those properties, then that happens. So this is planar dual. This is actually Fourier transform. So I don't know which garden party you have to be to impress somebody with this fact, but planar dual is actually Fourier transform in the 4 regular case, and that is kind of cool. Yeah, and there must be some garden party somewhere where you can impress someone with that fact. Okay, so the graph and its planar dual have the same period. All right, what else is true of these things? Well, there's a product property. If the graph looks like this, there are the external edges, then actually the product of these two. Whoop, that's not a very good blob. Okay, there's a better blob. And so just to be totally clear, this blob just represents, there's graph in here. I haven't, there's just some graph. And this blob, that's also just some graph. This is just some graph. But this is an explicit edge between those two verses. This is graph, just some blobby old graph, and this is an explicit edge. Okay? So there's a nice product property. Now, here's a cool one here's the one that sort of links the two sides together, which is that it doesn't actually matter which vertex you get rid of. So if you take k minus v and you take k minus some other vertex, then you have the same period. And this is actually a conformal invariance kind of property. So that's kind of cool. Okay, and that now means I could restate this on this side. So I'm now going to use, I'm going to write k tilde for k minus v where I don't care which v is, where I don't care about v. Okay, so rewriting this, remember I just take the external edges and I put a new vertex there. So now this is about a shape like this, connecting to a shape like this. These are still blobby guys. And you still have a product, but you just have to look what's going to happen. Well, there's that explicit edge. And then there are the ones connecting the external guys up to this other vertex. So you get an explicit triangle. And this is where it's now extra useful if I color in the blob so that it's a little easier to see which are explicit edges, which are those three, and which is blob, which is this. So that's just a restatement of that property. I'm going to write down one more and then I'll stop, but this isn't the end of these. So you said, okay, well, this is about 3 vertices. What about 4 vertices? And this is really cute. This is Oliver Schnetz noticed this one. You got to practice doing that drawing. You see what happened? There's a Klein foregroup action. Because I got these guys together, and now I take a matching of the vertices. Let's say I do these ones, and now I swap across the matching. And so there's a little Klein foregroup action there where I have, because there's the 3 different matchings, and I can do the whole doing it. Okay? So that's cool. This thing, this number that you calculate from the graph that has interesting number theoretic properties and also relates to the physics because it's a residue of the Feynman integral, and it's really capturing a lot of the kind of numbers that would show up even in general. So you can really say that it's capturing something important about the physics. It has these nice graph symmetries. And so you can ask now a new question. You can say, what other things, what other graph properties have the same symmetries? Because as soon as you find something else that has the same symmetries, then you have hope that that thing is going to tell you something about the Feynman integral. Because it's somehow behaving the same way. It's like a combinatorial avatar of the Feynman integral itself. And at this point, we actually know quite a few of them. So I've got just a couple of minutes left. So I'm going to tell you about a couple of other graph invariants with these symmetries. Okay, and I'm going to do it in 2 columns again, because some of them make more sense to state on the one side, and some of them make more sense to state on the other side. And the first one, this is another one where you got to put your algebraic geometry hat on. The first one was due to Oliver Schnetz and then studied by Oliver and Francis Brown. It's called C2. I'm just going to write it down at a prime, but you could also put it at a prime power of the graph. What is the definition? It's actually written over there in the list of combinatorial objects, although I guess it's maybe not as combinatorial. All right. You take that Kirchhoff or dual Kirchhoff polynomial, and then you say, I want to count points over the finite field with p elements. Okay, but now you say, wait, I don't have an algebraic geometry hat. What the heck does that mean? And it's actually super concrete because you just say, okay, I imagine, right, integers mod p, right? So 0, 1, 2, 3, up to p, minus 1, right? Plug in all of the possibilities from that set for your variables and see if it's 0 mod p. You are literally counting how many times it's 0 mod p. Okay, so that's a number. It turns out that if the graph has at least 3 vertices, it's always, and is connected, it's always divisible by p squared, and you take the result mod p. Okay, that's a thing. Why would you want to do that? It's a bit of a different story, but you have to ask someone with an algebraic geometry hat, and they will tell you that if those periods were always multiple zeta, then these should always be independent of p. It's basically a coefficient of a polynomial. Now, it's not the case that the periods are all multiple zetas, but this is a bit of a measure of how far they are from being multiple zeta. And it comes from this whole motivic story. Fine. It's a thing. This was, for a long time, only conjectured to have the symmetries. And in particular, this completion symmetry, the one that links the two sides, was only conjectured. But a couple of years ago now, in 2023, Eric Panzer and I finally proved that after it had been open for more than a decade. And how did we prove it? Well, we proved it using another invariant that actually links all these things together. And that is, you can take a diagonal coefficient in powers of this polynomial. So here's the polynomial, and I'm going to raise it to a power, let's say 2r, and now I'm going to look for r. I'm going to look for the monomial that would be the same power of all of the variables. And if you want 2r and specifically all of these to be r, then that will work as long as your graph really did come from a 4 regular graph like this. There are more general versions of this for graphs of higher regularities, but I just wrote down that one. It turns out this coefficient for any value of r also has these period symmetries. And that's actually much more provable. And you can connect these two together. And this one you could also connect to another invariant, which was this Martin invariant that Eric, well, he sort of dug it out of some old literature, but really I think you should say he thought it up in this context. So we're going to call it M. I'm going to define it recursively. So if the graph has a loop, or a self loop, let's say, so an edge where both ends are at the same end, we're going to give it 0. If the graph is just this guy, we're going to give it 1. And otherwise, you're going to pick a vertex somewhere in the graph. So that's a vertex, a 4 regular vertex somewhere in the graph. Notice we're over here on the K side. So this is honest to goodness 4 regular now. And now you're going to take the 3 different matchings around that vertex and replace that vertex with them. So here there's actually a vertex there. And now I'm going to say, well, what if I just connect it up this way? Or what if I connect it up this way? Or what if I connect it up the non-planar way? There's actually no planarity here, so. Okay. So you say there is in fact a unique graph invariant that satisfies these properties on a 2K regular graph, or I drew it for 4 regular. You can generalize for 2K regular. And it turns out you can phrase this in terms of this guy, and you can phrase this guy in terms of this guy with a couple caveats. I mean, the proof does take a while. But notice, this is on the K side. So completion is automatic. There's no completion, right? We're already completed. And here, you've removed the vertex. But there's a concrete expression for this in terms of this. So the vertex doesn't matter. And that's the proof of completion. But this opened up a whole world. There's a bunch more invariants. You can count the number of 6-edge cuts. That's a really nice invariant. There's an older one that one of my students made where you take the sign incidence matrix, you stack them up and you take a permanent and you think permanents, those are terrible. But in the right context, if you take it modulo P and you stack up P-1 copies, they're actually nice. And so there's this whole slew of invariants that tell you stuff, and I have 0 minutes, but I'm going to just say one thing without writing. So part of why you care about this is I said, at some level, it's a game, right? You say you could just, I'm looking for things that have that invariant. But then ultimately, I would like these to give back and let me calculate something about the Feynman integral. And there's already some evidence. C2, for instance, tells us whether the transcendental weight is looking like it's going to drop. Now, a lot of that's really just conjectural, since transcendental weight is pretty well impossible to get a rigorous handle on. But there are some rigorous statements you can make in that direction. It's certainly telling you something in that direction. But there's more to it than that, because these sequences that you get, right, this is a sequence depending on R, and similarly make a sequence out of these guys. So there's some really nice new work of Francis Brown and Eric Panzer, where they take that sequence, they see it satisfies a recurrence, they look at other sequences that satisfy that recurrence. You can build an a priori limit, and you can get the period back. Now, there's a lot of details, and I think we need to wait for them to write the paper. So next time, if you think that's super cool, you should go talk to them, and you should tell them, write that paper already. But I think this is the first place where we're really seeing something that's pure algebra and combinatorics, and it has some promise to actually pull out the actual numbers. And to me, that's super exciting, because that's really what I want to do. I don't want to do any integrals. I just want to do some combinatorics and still tell the physicists what they want to know. Thank you.
Thank you. Yes, now it's better. Thanks a lot for your talk. Are these invariants that you also see in knot theory? This type of invariant? It looks like a Young-Baxter equation type thing. I'm not exactly sure how to make a rigorous connection. There's certainly something very similar. Yeah. Notice that these graphs don't have a planar structure. So the fact, I know I said when I was writing them down that this was the non-planar one, but that's not really fair, because there's no intrinsic planar structure here. I'm really just taking the 3 matchings, and you'll notice they're all with the same sign. So it is a little bit of a different story, and I don't know how to make a rigorous connection, but there's certainly some at least aesthetic similarities. Okay. And then another question, but probably it'll show I haven't really understood. So your approach, combinatorial approach, can it give an insight into relations between multi-theta values?
I mean, there's pretty solid conjectures of what the answers should be there. So
no, but from this combinatorial approach, does that?
I mean, in principle, you can.
Do these symmetries give you a new insight on
I don't think they give you new insight. You can see some things that were already known. I don't believe you get any new insights. Yeah, I'm going to stick with that. I don't believe you get any new insights.
Okay, thank you.
So I believe this whole story is for 4 regular graphs. Can you do, for example, 6 regular graphs and etc.? Is it?
Yeah, so it depends. So that there's 2 answers to that. One answer is, yeah, so let's say we're sticking, yes. So for instance, you can calculate the periods in phi cubed theory. And Oliver Schnetz and I think Mishi Berinsky is the other person, but possibly it's someone else from that same crowd, has done a bunch of those computations. You can look for the sort of symmetries you get. And in fact, that's what this is about. So this you might recognize as looking like the delta y operation. So here's a triangle and it's a doubled y. This preserves 6 regularity. And there's a really interesting connection between the 3 regular and the 6 regular, where you basically think of 6 regular as being 3 regular where all the edges have half weight. Anyway, the point is, yes, you can tell this story. You get a different family of symmetries, but there's still many nice graph theoretic symmetries. And some of this part, like for instance, Martin, I only wrote Martin out in the 4 regular case, but you can easily guess what the generalization is. This is still 0. You have to put the correct number of edges to make it just be 3 vertices.
and otherwise symmetric. And here you would sum over all the different ways of matching, of choosing a perfect matching of the vertices around of the neighbors of a vertex, neighborhood of a vertex. So this story and many of these symmetries immediately carry over to higher even regularities. Now, there's a slightly different question that maybe is like a physics version of the question, because you could ask for something mixed, where you've got like a 5-4 and a Yukawa interaction, and you could ask about that story. And that's a lot newer, but Oliver Schnetz has done some of the initial period calculations there, so there's still a well-defined period that you think of as the residue of the Feynman integral, so you can still make a table of numbers, and that's how all of this started, where someone who's good at those computations makes a table of numbers, and you start to look for the patterns. And so, yeah, that's been, there's 1 or 2 papers in that direction. And yes, again, you're getting some graph symmetries. They're not quite the same ones. It has not been investigated in nearly the same depth, but there's definitely some kind of story there.
More questions?
Can you hear me? In the graph theoretic expansion that you did of Feynman diagrams, there is also another kind of expansion using amplitude, this Nima Arkanihame, this one. How does these two relate? Like, see positive geometries come?
Yeah, I don't directly see the positive geometries. So there's, I mean, that story works the best in the N=4 super Yang-Mills case. Now, I know it does go beyond that case. And this sort of works the most neatly in these scalar cases, but then again, they got to meet in the middle, right? Because the actual standard model's here in the middle, and we got to be able to get there both from our 2 different directions in the end. There's a couple of other ways that it's a little bit different. So a lot of that is about playing games with integrands, whereas here we are actually doing the integrals. And so in that sense, this approach is more powerful. Now, on the other hand, they're always working in this on-shell or BCFW kind of context. And so in some sense, that's more physical. So that would be a plus for their approach. So I guess at this point, they're still somewhat complementary, I would say, and the strengths, they have different strengths. In the end, we're describing the same physics, so they got to meet in the middle somewhere.
So we'll have a short comfort break for 10 minutes and be back here at 10 past 10.